Okay, let's start. Do you have any questions? Okay. So, hello, Sagar. To start from where we left off last time we were discussing the supplemental section N4, right, which is not in the text, is in the department, on the department's website, the supplemental notes, right? So if you go on that website, on the link on the syllabus, you'll see the notes for this section. So the idea, right, the main message from the discussion, by the way, right, the topic is obviously matrix exponentials. The main message is if you look at a system y prime equals to ay, okay, and doesn't matter what a is, okay, doesn't matter what a is, and any size, okay, any size, a n by n, and you're given the initial condition. Right, then the solution, right, to this system is y of t is e to at y0, period. Okay, so you see this is the beauty of this result from a mathematical point of view, because at least it gives you one way, okay, to represent the solution. All right, and it doesn't require you to go into, you know, asking if what kind of eigenvalues, eigenvectors does A have, right? And if, especially you see if the larger the A, right, the harder for you to deal with the eigenvalue, eigenvector approach. I mean, not harder, but the more complicated, right? The more complex. So of course the price to pay, right? So this gives it gives an abstract answer, right, to all questions, right? Abstract representation, right, to the solution, right, to all system, right, of linear equations, linear first order ODE, right, with constant coefficients. Okay, so obviously here there is something more than just writing e to at, right? E to at is defined by the power series, right? It's defined by the sum, right? K from 0 to infinity of a to the k over k factorial. Sorry, right? E to a, just a matrix A, because the t there is just a scalar, right? It gets absorbed into a matrix. So e to a, or if you want e to at, then you can just do at to a k like this. Okay, so obviously, right? So that is just a pure description, abstract description of what this object is. It's not for computational purpose, right? So this is not, right, not the best way, right, to compute explicit solutions. Okay. In other words, our eigenvalue, eigenvector approach is still, I guess, the most efficient way to do so. On the other hand, right, what do I want to say here? So as far as, I don't know, right, the final exam is concerned, so if I ask, right, so I just want to give you a note that if I ask you, right, if you're asked to solve like a linear system, right, on the exam, don't give this answer, okay? In other words, I'll be more careful and say give explicit solution. All right. In other words, this is an okay approach, but unless you compute out what e to at is, I'm not going to accept this as a complete answer. Okay. So don't do that. If the question, because like it's almost like you can just give this answer for any system I ask. All right. But what I will ask, okay, is a separate question, just pure like separate question. You will have a separate question on how to compute e to a for some given a. Is that okay? So in other words, I will ask an exponential matrix exponential question. I give you an A and I ask you to compute e to a. All right, tell me what it is. But if it's a system, right, do use the eigenvalue, eigenvector approach. Our discussion here, again, right, has mathematical content, has mathematical value. But, right, I don't want you to go around using this for computational purposes. Question here. So to round out things, right, several things I want to tell you. So first, right, I want to tell you that, so tying up loose end. Oh, okay, so sorry, right? Let me tell you, of course, how to compute this to begin with, right? If I ask you to compute this, what do you need to do, right? To compute e to a, right? To compute e to the a practically, you need to basically the type of matrix that can be computed, right, for the exponential the most efficiently is the matrix that is diagonalizable, okay? PDP inverse. So this happens if A, right, has a full set of eigenvector. All right. If A has a full set of eigenvectors, then A is diagonalizable in this form, and D will be the eigenvalues, and P will be the eigenvectors. All right. So you must match up the eigenvalues and the eigenvector correctly. So this is an eigenpair, right? This is an eigenpair, for example. But if you match them up correctly, then, right, you will have decomposition like that. And then, right, e to a in this context will be p e to d p inverse, which if you raise a matrix, a diagonal matrix to the exponential is just this. All right. So your work in computing e to a will involve, right, calculating eigenvalues, eigenvectors clearly, and then, right, calculating this inverse of the matrix formed by the eigenvectors, and then multiply them together. But I guess the multiplying together is not too bad, right? So that's how you would do that. Any question on this? Okay. So tying up loose ends. So several things, right? First, I want to show you, right, that this system indeed has solution y of t to be e to at y0. Okay. So what do we need to check? First, we need to check the initial condition works. So the initial condition is e to the zero matrix, right? This is a zero matrix, not the zero value, right? It's a zero matrix times y0. But e to a zero matrix, as you can easily verify, is the identity. So that's the identity times y0, which is y0. So the initial condition checks out, right? Now we need to verify that under this form, y prime is equal to ay. So y prime under this form, right? I'll make you a deal, Sagar. If you can compute that precisely, okay, for non-trivial A, like 1, 2, 3, 4, or something like that, then you get an A for the course without having to take the final. Deal? In that form. You can take all the time you want. The point is, right, how can you raise the matrix to a high power without doing a lot of computation? Okay. So the next question is to see how to do y prime equals to ay, right? So obviously, right, you expect that, well, you see, if you differentiate this form, right, you expect that y prime is equal to a e to at y0, right, obviously, which, right, would be a y, because this is y. But, right, again, for those of you who are mathematically oriented, do not take, formula for granted, right? I mean, you may think, yeah, of course, why not? You differentiate exponential here, you should get a, right, in front, just like the chain rule. Yes and no. Yes, the beauty of it is the chain rule you learned apply in the matrix case, but no in the sense that without some careful thought, right? You cannot know that the rule you learned in the scalar case apply in the matrix case yet, right? Because here, after all, this is a matrix, okay? What do we mean when we differentiate this, right? How do we know that, for example, that like the when you take the difference quotient or whatever that is, right? In what sense are you getting this? Okay, so all I want to say is this is not trivial. In other words, making sure that differentiate with respect to t like this still works, okay, in the matrix case. And I mean, all right, so there's some details that we will fudge over here, but by and large, right, you have to appeal to the definition, which is exactly what Saga wrote above, right? This definition. So we need to appeal to the definition. So that is differentiate the sum, right? A to the k, t to the k over k factorial. All right. Now, what we will fudge, the detail we fudge about here is we'll transfer the differentiation inside the sum. Okay. So this is exchanging differentiation and sum, which actually in calculus you do all the time. When I say we fudge the detail, the reason why we fudge the detail is because this is an infinite sum. And some of the time you cannot do this, okay? Some of the time you cannot do this. Here we can, but why this is true is not something we address in this class. That's like a real analysis question, okay? But anyway, I will switch this, and that's the only thing that, we won't explain explicitly here. Okay. But then you see, right, differentiate here with respect to t is the usual one, where you get a to the k, t to the k minus 1, right, over k minus 1 factorial, right? Because when you bring down the k here, dividing by k factorial, lower the factorial down by 1. But for that, right, our sum doesn't start from 0 anymore, but it starts from 1. Okay, you see? Because the 0 term, right? The 0 term is just the identity that get differentiated to 0 anyway. And also when you do 0 minus 1, that doesn't make sense, right? You have to start the sum from 1. Any question here? Okay. Then this will be, right? I take out one single a. I got a to k minus 1, t to k minus 1 over k minus 1 factorial. Yes, Sagar, but when here is for very, very abstract mathematical discussion, right? To understand the structure of this object, not for actual computation. You see the difference between the two. I mean, roughly you can say that one is like the theory side of math and one is the computation side of math. On the computation side, you don't necessarily use a theoretical tool to do computation. All right, so then, right, I will do a change of variable. Instead of k minus 1, I just do a k. But then, right, the cost of this is I move this summation back to 0. All right. But then you recognize that, right, this is exactly e to at as required. Okay. And I think Carl, right, among other people, asked if the sum starts from 0 or from 1. This is, again, right, a highlight that the sum does start from 0. Because, I mean, of course, they're the same sum. But, I mean, if you start this from 1, that's not e to at, for example. Any question? All right. So the second I want to address is really not a topic of this section anyway, but on diagonalization. So I want to explain why A is PD P inverse, where D is the eigenvalues and P are the eigenvectors. Does anyone know? This is really a linear algebra question, not a question for this class. But I think because this structure is quite important and you see it in many places, just kind of want to quickly explain to you why. Oh, I'm just asking, why if I have D and P like this, then A is PD P inverse? I mean, magic? What's the reason behind that? No, Will, that's the practical reason. I mean, like, what's the goal of doing this splitting? I'm asking why this splitting is true. In other words, why if P and D like this, then the splitting can work. I'm not asking for the practical application, right? I'm asking why this is true, right? After you know it's true, then yes, you can use it for some purpose. But why is this true? Okay, so let's see. First of all, right, the fact that P inverse is written should exactly, right? So the key is PD is AD, AP, right? It's same as AP, right? So first, I'm not sure what V are what we're talking about here. You mean AP, but then you're not explaining it because I'm not sure you're saying something like, so yes, the goal is to prove that AP is equal to PD. All right, but why? Why is that true? Yeah, No, 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 no. You are very sloppy. You are very sloppy, both of you, in terms of linear algebra. You cannot you cannot do this. I don't know what then you cannot do this. A PP inverse or something like that. But but then if you do that, right? I'm not sure what you're saying, but then you're saying A is D. And plus, I don't see where this calculation comes from. So yeah, what you're saying? I don't see how PP inverse is I, which is true, enters into this question actually. All right, so to save time, all right, let me show you. Correct. Yeah, so no, right? And even if you shift things around, it's not. Yeah, but what identity are you showing, Daniel, right? I mean, I don't guarantee you the idea here has nothing to do with PP inverse equal to I. Okay? The idea is this, that you must look deep in, because pay attention to what you use. If you just use the fact that PP inverse is I, then any structure of P would work. Why do we need P to be the eigenvectors, right? Clearly, eigenvectors play a role. So if you don't invoke the eigenvector, eigenvalue idea, then somehow, right, what you're explaining misses something, okay? So here, right, exactly, you require strongly on the eigenvalue, eigenvector structure like this. On the left-hand side, you have this. On the right-hand side, you have this. Okay. So it's all about trying to see what the left and right hand side are in terms of their structure. On the left hand side, basically it plays on the idea of block multiplication. I'm not sure you ever hear about this, but it's a very, very strong and useful idea. Basically, it says that as long as things, the dimension makes sense, then you can just treat elements in a matrix as a block. So here I treat A as a scalar and I multiply it in, even though I know A is a matrix. But here it works because AV makes sense. In other words, here the left structure is AV1, AV2, AVN. Okay? And pay attention, right? It works because AP is a matrix, right? A is an n by n matrix, P is an n by matrix. Here, AV is a vector, an n by 1 vector column. So a column, a column, a column together is really a matrix. So yes, right, this is this. How do I take care of this? Here, I take care of it like this. I look at this as a row times a column, a row times a column, a row times a column, okay? Again, right, it's not exactly that because I know, right, each of them is a vector. This is a scalar, that kind of stuff. But block multiplication make sure that you can do that correctly. But anyway, if you do this times this, what do you see? First row, first column is lambda 1 v1. First row, second column is lambda 2 v2. So on and so forth. And now we check, right? These two matrices are equal if each of their columns are equal. So we need to check that AVI is equal to lambda IVI. But that's true by definition of eigenpairs. And that's the reason. Any question? Is this okay? All right. When you consider it mathematically for definition, not for computation. Yeah, that's it. You can get an approximation, but you have to think of how much work you have to do for that approximation. And again, right, if you have a diagonalizable structure, then this is a much preferred calculation than summation. Summation is a definition, okay? I mean, many of you who study physics or math should have an appreciation of definition, right? Definition is where we get off the ground, where we define the object. But then, of course, once you have the object, then you want to have easier way to handle it, right? Which comes from its properties. But right, don't confuse definition with properties. Definition is where you give the object a structure. But you don't necessarily use the definition every time you deal with things, right? You may use some other properties that make it easier to deal with. All right, this is it for matrix exponentials. Any questions before we move to the next topic? All right, so next topic I want to talk about is 3.6, second order homogeneous linear ODE with constant coefficients. Which basically talks about equation of this form. Okay, which we have discussed before, all right? So I'm not here to repeat the solutions, all right? Look back into the lecture. So we have discussed this, in terms of solution, in terms of general solution. So to give you a quick overrun, right? Basically, you need to look at the characteristic equation. Okay, and you solve for lambda. If lambda 1, right, lambda 2 are real solutions, then your y is C1 e to lambda 1t, C2 e to lambda 2t. Okay, notice how this is quite similar to what we get, with our system, right? With our 2x2 system. If lambda, right, is, a plus minus bi are complex, then, oh, sorry, right, I use a and b up there, so what do I use here? Oh my gosh, A, B, C, D, E. I'm running out of notation here. What should I use? Can use A and B again? Don't be confused with the A and B up there, right? Just different A and Bs. So then y, right, is e to at, right? C1 cosine bt plus C2 sine bt. Okay. And finally, right, if you have repeated roots, lambda equals to, right, lambda 1 equals to lambda 2 equals to lambda, right, repeated case, then you got y of t is C1 e to lambda t plus C2t to lambda t, right? Simple. So this is just the way you solve it. Now, what I want to discuss is a particular model here, okay? The model of, so application, model of harmonic oscillators with damping, okay? So again, right, the idea is basically you have a spring, right? A spring with some spring constant K attached to a mass, right? A mass M. So spring constant K. Also, this is, submerged in some kind of damping viscous solution. So basically, somehow this, to make it more fun, right, is immersed in a liquid or something, right? Or air, I'm not sure if air, yeah, air has some damping coefficient, I think, but negligible. But so basically there's a damping coefficient. What is it? Damping coefficient B, okay, like the book mentioned. So K spring constant, mass M. So Newton's second law says F equals to ma, right? So if you let y be the position of the mass, right, away from the equilibrium, which we denote by 0, okay? Then F, right, so then A is y double prime. F, right, consists of two forces, the spring constant, which oppose to motion, so it's minus ky. If y is negative, right, then it push, forward. If y is positive, it push backward. The damping also push away from motion, but sorry, against the velocity, so it's going to be b times y prime. Okay. So all in all, right, the model for harmonic oscillators with damping coefficient, or sorry, with damping, right, is basically a second order linear ODE where, so it's not the special thing is not about a second order linear ODE, but where the coefficients M, B, and K are all positive. Okay. So here, right, it has some physical, the solution has some physical properties, right, that we can infer from the parameters, right, of the coefficients. That will be interesting. Okay. So that is the model that we want to discuss. Any question here? Okay. So again, right, the solution approach is that we look at the characteristic equation, which says m lambda square plus b lambda plus k, right, is equal to 0, where you see that lambda then is going to be plus minus b, sorry, negative b plus minus, right, square root of b square minus 4km, right, over 2k, 2m. Okay. So you see that the nature of the solution, right, depends on how the damping coefficient interact with the spring constant in the mass, right? But either way, you see, because B is positive, right? Because B is positive, and M is positive too, right? So minus B over 2M here is going to be negative. So your solution, right, whether real or complex, depending on where these coefficients are, it will always be your solution, right? Doesn't matter what it is, y of t will go to 0. as t goes to infinity. Is that okay? So here, right, in the presence of damping, you will settle back into equilibrium, right, as time goes on. That's what the model says. And of course, right, that accords to what we know about how the spring behave. Sorry, how the spring mass system behaves, right? So as long as, right, again, as long as damping is present, then you will go to zero, right? The mass will stop at equilibrium as time goes on. Nothing surprising there. But so different cases, right? So when you have b squared minus 4km is positive, okay? When b squared minus 4km is positive, then this is called overdamping. Okay, because the solution is you have both lambda 1. Oh, here, yeah, here's a case. So here lambda, right? You got lambda, actually it's lambda 1 and lambda 2. One of the things to observe here is that when the case where this is positive, I claim that both of my lambdas are negative. Can you see that? Right, both of the lambdas here are negative, okay? Not just one. What's the reason, right? The reason is, so lambda 1, which is minus b minus square root of b squared minus 4km, this guy clearly is negative. But the second one, right, which is this. So you have a negative number and you add a positive number, right? How do you know that that number is still negative? Well, you know this, right, from the fact that b is bigger than square root of b squared minus 4km. Right. Correct, exactly. So therefore, right, actually, if somehow this guy is positive, then we're in trouble. Then it's not clear that the solution will go to zero as t goes to infinity, right? In fact, you see here, right, what happens is you have your solution like this. C1 e to lambda 1t plus C2 e to lambda 2t. And both lambda 1 and lambda 2 negative. You can see that yt goes to go to zero, right, as t goes to infinity. And I may say very quickly, okay? Of course, that's a qualitative statement, so we cannot, well, we can make it more precise, but basically, in the present, pay attention, this has a lot of physical meaning. This is not just math, all right? This is modeling. Here it says that the coefficient of damping is quite large, right? How large? It's larger than this, right? I mean, relative, right? Of course, everything is relative to the spring constant in the mass, but here the damping constant is quite large. And for that matter, right? So a favorite thing that I learned from the other class that I taught, 244, is that in this case, what happens is, let's say you start here, okay? You can swing like this and then go, or you can go like this. I don't know. So this is the equilibrium. This is how the spring swing, right? But in overdamping, a very fun fact, and I think critically damping too, which we'll talk about, is that the equilibrium position. Oh, sorry. Yeah, it's fine. There could be negative there. Is crossed at most one. Okay. So even though, right, it's a spring, so you expect a back and forth kind of action. If you have a lot of damping going on, then it's going to swing back at most one time and then slowly settle into equilibrium, or doesn't even go there at all. So yes, I mean, there could be one, right? So, but it's hardly qualifies as oscillation, but that's fascinating, at least for me, that when damping, right? But you can imagine, right, the situation very, very clearly. When oscillation, when you have a lot of damping, right, and how much it's a lot, right here again, right, compared to the spring constant, right? So here, damping wins. Then there's no back and forth action for you. It's just boom and then back, that at most, or just slowly settle back. Okay. And then the second situation, right, is when this is zero. Okay, this is zero. Oh yeah, yeah, of course. I think actually, you know what? My physics education somehow stopped at mechanics. I mean, I did take electromagnetics, but I don't remember anything there. But I think the book when I taught the other class mentioned, the what's this, what do you call it? Like there are three devices: inductor, yeah, capacitor, that kind of thing. With second order system, same thing. I cannot tell you much more about that because I have no idea. But basically, somehow I do remember that the system is this. Oh, sorry, the equation that governs it is also this, where I think this is the V, right? And the potential or something. I'm not so sure, but yeah, RLC circuit exactly. Yeah, yeah. So yeah, you can have damping there too, but I have no idea what damping means in that sense. But here physically, I can see what's going on. Yep. And the analysis, right? And this is the beauty of math. I mean, if I may advertise it. So is that, as long as the equation fits, the phenomenon works in the same way, whatever that is, you know? So yeah, I mean, outboards, I don't know. I mean, I guess one application I see is exactly if you can control the damping coefficient, right? Which I think is the resistor. I don't know. Is then you can control how your system behave by dialing up the damping or dialing down the damping. I don't know. That could be one way. I don't know what you control though, but that could be one thing you do. So the second case, right, is called critical damping. Right? So this is where, right, that thing is 0, b squared equals to 4 km. All right, so here you have the repeated root minus b over 2m, right? Lambda 1 equals to lambda 2. And yeah, even though this is this, right? So, but clearly the solution is this. And both still negative, right? You got a t here, but that doesn't help you much, like that. So maybe if I can do, right, this is actually minus b over 2m, right? Like that. And the behavior of the system is the same thing as this. Like this, also equilibrium is crossed at most ones. So I may be mistaken here, maybe over damping, you cannot cross equilibrium, I forgot. It all depends on whether you can prove that C1, C2 here must both be positive, which I'm not so sure. But if you can show the C1, C2 here must be both positive, which I don't think see why, right? But if they're both positive, you see, because then both of these are positive, so you cannot cross at all. You can only do this. But even if one of them is negative, you can only cross at most ones. Okay, so equilibrium also cross at most one. Oops, sorry. And then, right, the last case is under damping, where you have b squared is less than 4 km. So here, right, you do have true oscillation. because then, right, basically your solution is, so lambda, right, is going to be minus b, right, plus minus square root of b squared minus 4km over 2m. So this right here, right, will be your imaginary part, right? That will be the exactly, that will be the omega, right? That will be the, well, roughly, right? That will be the omega for your, that over 2m, right, is the frequency, right, for your oscillation. So your solution here will be, right, eta minus b over 2m times t, C1 cosine of, right, let's say omega t, plus C2 sine of omega t, where omega, right, is the other way, right? Square root of 4km minus b squared, right? Because now this is positive over 2m, right? So I think that's called the natural frequency or something, right, of your system. So first, right, the oscillation, the picture will be something like this. So you will have oscillations, right, but smaller and smaller, right, down to 0. My picture is not, right, down to scale, but it's basically enveloped by eta minus 4m, right, t, and then this, right? And then how quickly you oscillate in between, right, depends on this guy right here. The larger this guy is, right, the more you oscillate. So clearly, right, the higher the spring constant and the smaller the mass, for example, just how this relatively play out, the more you have the oscillation going on, okay? Any question? Yeah. So Lauren, what are you asking? You can't read that. KMT, no, my bad. Here, 4 over 2m, right? Is 4, oh, yeah, it's 4, hold on, I can't even read my handwriting. What am I saying here? B, right? B. Sorry. Thank you, Lauren. I can't even read my own handwriting. B over 2m times t. B because it's, you know, the middle coefficient, right? Right here. Yeah, sorry. Yeah, so this is the amplitude change, right? Exactly. This is the amplitude change, and this is the frequency constant, right? All right, question? So, right, I think I just want to mention this particular example, right, of basically, again, mathematically is an example of what? Of a second order, you know, linear ODE, right, with constant coefficients. But of course, right, the emphasis here is with the modeling part where you interpret, right, the solution according to a physical system here, right, a spring mass system in a damping, right, environment, or you can interpret it as an RLC circuit if you know what that is, right? I don't, so I'm not gonna comment on that. Actually, in this class, this is where we stop because we don't discuss the how to solve it with, you know, the right hand side being non-zero, right? But in 244 we get there, and actually this is quite cool because if you look at this, then you have a chance to discuss the phenomenon called resonance, right? Where because you have a driving right hand side, you could make the spring mass system oscillate way out of whack, right? If you have the frequency of the driving force the same, right, as the natural frequency of the system. Okay, So you can look into that if you're interested, or you have already seen that in your physics class, for example. But here we don't go into that. All right. Questions before we move to the next topic? All right. So next one I want to discuss is the parallel idea of bifurcation, but now in the system. All right. So the title here is called the trace determinant plane. Okay. But actually the real point is, bifurcation in 2x2 system. Okay. So let me give you an example, and so you see what the point of the question we consider is. So we always consider, all right, y prime equals to ay here. And here the matrix A, unlike the other cases we consider, depends on some parameter. Okay, so a unknown parameter, undetermined parameter. Okay, so what we want to do is to describe or to see, right? I mean, basically, question is how does the system change? Okay, of course, in terms of is phase portrait, right? And equilibrium classification as A changes. All right. And then also, obviously then, right, what is find critical, right, values of A, where significant change happens. And these critical values are called bifurcation. Yes, Daniel, but it's more subtle than that. Okay, it's more subtle than that. It's not just where lambda changes sign, because that would mean you change from sink to source, for example. But here you have more, right? More ways of changing. For example, change from real to complex, from distinct roots to repeated roots. All of those are changes, right? So in fact, we have more change than just sign. Yeah. So these are called bifurcation. Okay. And so, yeah, like roughly like Daniel said, but he was just thinking of one way to do it. We want to systematically describe a way, right, for you to control, right, to see how to approach this question. And so for that, right, let's just look at a matrix in general. A, B, C, D, all right? So I guess what are the eigenvalues, right? In terms of A, B, C, D. Well, I mean, you see, right? Basically, you do A minus lambda, right, times D minus lambda, right, minus B times C is equal to 0. Okay? So if you rearrange this, you got lambda squared, right, and then minus A plus D lambda, right, and then plus AD minus BC equal to 0. We have a better name for this. We call this lambda squared minus T lambda plus D equal to 0, where T stands for the trace of a matrix and D stands for its determinant. So it's quite a cool structure when you think about it, that basically the quality, right, of the lambda, right, of your eigenvalue in a 2 by 2 matrix gets completely determined by its trace and the determinant. So by the way, right, trace is basically sum of the diagonal terms. So here, right, A plus D. So that's why, right, it's called a trace determinant, kind of study. But that's where it comes from, okay? And so, right, you see then in terms of T and D, we got lambda is T, right, plus minus square root of T squared minus 4D, right, over 2. And so what do we see, right? We see that basically you will see a typical tool. The tool that we use is called the trace determinant plane. Or can we call it TD plane? That sounds like a vaccine, right? I don't know, TD plane, touchdown. Anyway, right, TD. The reason, right, is because you see one of the critical object is when this is 0 or not. So exactly, right, the parabola of, right, D equals to T squared over 4. Yes, or, if you want, this is just basically T squared minus 40 equal to 0, will be important for us. So let's say that looks like this. So if you are above the parabola, right? So if you're above the parabola, then is this negative or positive? Pay attention, right? T and then D, that's the convention. If you swap things around, you get completely a different picture. So pay attention. Trace determinant, so that's why X and Y, okay? Trace determinant. But so if we are above here, do we get negative or positive here? Negative. Yep, because D is bigger, right? D is bigger. D is the y-axis. So this is negative. So this is where you have the complex domain, right? Here is where you have the positive domain. Or, sorry, complex domain and real domain, right? So that's one, right? That's one boundary that you want to pay attention to. What other boundary you want to pay attention to? T, right? This decide whether things are sink or source, isn't it? Right? Because if it's positive, is source, whatever source it is, right? I mean, roughly, of course, I'm not saying strictly that, but right. So T being positive or negative will decide that. So where is it? T equal to 0 is this line, right? So T being positive or negative will decide that, right? So that's one more. Okay, here, right? And here. Also, right, whether D being negative or positive also change things. Whether D being positive or negative also change things. Okay, so what I'm trying to say is I'm pointing out to you the critical lines where behavior change happens. First, this one. Second, this one. And third, this one. Okay, this controls whether solutions are real or complex. This roughly control, single source up to a point. And then, right, what does this control? This is where d equal to 0 or positive or negative, right? Well, actually, you may think d equal to 0 doesn't change anything here. It does. In what sense? Well, so notice, right, everything below here are real solutions, right? But when d equal to 0 is quite important, because d equal to 0 means you have lambda equal to 0 is an eigenvector. Eigenvalue, I'm sorry. Remember the lecture last time, right? We say if the determinant, right, the eigenvalue equal to 0, if and only if determinant equal to 0. But remember, if you have lambda equal to 0 as an eigenvalue, you have infinitely many equilibriums. So, right, I do think, right, the book somehow doesn't seem to highlight this, but I do think this is a change. Now, what other change do you have? For example, if d, right, if d is positive, okay, if d is positive, then you see that basically t minus square root of t squared minus 4d, right, will be, so, okay, what do I want to say here? You know what? I think it's easier if I want to, if I do this. So we have one value on parabola. Yeah, if right on a parabola is when you have repeated eigenvalue, because that's when this is equal to 0. Okay. So what I want to highlight is this, and this are lines that you want to pay attention, okay, as you see. But first, let me write down, right, the classification of the regions, and then we'll explain it. I think it's easier that way. So trace determinant, okay, TD. Okay. So there's 1, 2, 3, 4, 5, and then 6. There's 6 regions, okay, in the book, corresponding to, oh, sorry, 7. Sorry, this is 6 and this is 7, corresponding to different types of, behavior of equilibrium that we talked about before. So let's go through them to see if we can classify. What do you think 1 is? So by the way, right, let's look at this. So we have the solution, right? Lambda is minus t, right? Let me see here. Sorry, plus t. Plus minus square root of t squared minus 4d over 2. So what do you think, what region 1 is? What I'm referring to is things like, spiral sink, spiral source, sink, source, repeat eigenvalues, repeat eigenvalue sink, repeat eigenvalue source, what else, like saddle point, that kind of stuff. So what do you think 1 falls under? Spiral, yes, right. So first of all, it's spiral because t squared minus 4d is positive, negative, right? So it's spiral, complex for sure, but yeah, exactly, spiral. And single source, well, 1 is for t positive, right? So that is a source. So yes, 1 is spiral source. right? Okay, spiral because t squared, right, minus 4d is negative, and source is because d is positive. Sorry, t is positive. You know, so this, right, this is because it's above parabola. Yep. So then I guess you can see what 2 is. What's 2? Spiral sink, exactly. Same as 1, only with t negative, right? What about 3 then? Exactly. Okay. What about 5? So, ooh, I erased it. I'm not sure, right? I guess I should have more, right? I think there's an 8 here even, right? Because these guys are different. No, careful, right? So yes, so first 5 is source and 6 is sink. That's correct, right? Why? Because these are real, right? These are real, and these are real, and hold on, right? It's not quite clear yet. So basically 5, 7, right? All these guys are real eigenvalues, right? But to distinguish these guys, you must know if it's like the same sign or opposite sign. Yes. The distinction between these regions are whether or not the eigenvalues are the same sign or opposite signs. But I guess maybe before we do that, right, let's address the easy guy first. Let's address 4 and 8. What's 4? Yeah, that's right. Yeah, you're right. So, but we'll get there, right? I want to kind of more carefully do it. But what's 4, right? 4 is repeated, right? Oh, I should have done 4 on right there, right? 4 is where you have the line, right? So 4 is you have repeated, right? And that's source. 8 is repeated, sink. Is that okay? So now to decide 5, 6, and 7, okay? What we need is, so they're both real eigenvalues. What we need is, right, to check the sign, okay? Sign of eigenvalues. In other words, same or different. And how do we tell? How you tell is this. To check the sign same or different, you do lambda 1 times lambda 2. Because if lambda 1 times lambda 2 is negative, that means they are opposite sign. And if they're positive, that means they are same signs. Is that okay? Now, what's the product of the two? The product of the two is a product of these two guys, right? So that will be t plus minus there. So it's t plus square root of t squared minus 4d times t minus, right? Ignore the 2. Ignore the 2, right? But you see this is t squared minus t squared minus 4d. Whoops. So I know this, right? By the way, I know that when I take out a square, right? This is this because I am below the parabola, right? This is because I'm below the parabola. So that's why t squared minus 40 is positive, right? So of course this is equal to 4d. So you see, right? D exactly control the sign. Yeah. D, right, controls the sign of the product of the eigenvalues. So you see right here, when D is negative, that means they have opposite signs. That's why both of these regions are D, right? Or like, like Daniel was explaining, right? You can do that, or you can just look at the product. So if D is positive, D is negative, right? When D is negative, this whole region, the two lambdas have opposite sign because of this. And so that's why 7 is saddle. Is that okay? 7 is saddle. Also pay attention, right? So well, I'll get back later. But so maybe let me clarify like this. So the important boundaries, right, is this parabola, this, and only this part. Okay. Well, for the reason that if over here, if you cross from here to here, it's saddle to saddle. So nothing changes. Nothing changes. Is that okay? So when we say the line, right, the line d equal to 0, it's only up here. Oh, sorry, the line t equal to 0, right, is only up here. Right, down here, it doesn't change anything because if you go from here to here, it's still a saddle. Okay. But so that leaves you, right, with 5 and 6, you know that they have the same sign, right? You know they have the same sign. But then of course, if t is positive, right, then for sure one of the eigenvalues is positive. Then clearly the other one also is positive because you know they have the same sign. So 5 is source and 6 is sink. Any question? And so, right, let's go back to our example. A equals to minus 2a minus 2, 0, right? That's the example that we talked about. And you can have many a's, right, that we'll do for next class. But the strategy is this. For any given a, right, you sketch the TD curve as a parametric curve depending on a, parameterized by a. Okay, that's step 1. Step 2 is you check the intersection of the TD curve with the critical boundaries. How many critical boundaries do we have? The parabola. What is it? T equals to 4d squared, right? Or 4t equals d squared. T equals to t squared minus 4d equal to 0, right? T squared minus 4d equal to 0, that parabola. the t-axis and the positive d-axis. Okay. So these are bifurcation values. All right. For example here, right? For A, what is T? T is -2. Right? What's D? D is 2A. Right? So what's the TD curve for this guy? Maybe I should draw it a little bit lower. This is the critical region, right? Oh, sorry, this is the boundaries, right? What's the TD curve for this guy? It may be too simple to observe, but it's just a straight line t equal to -2, nothing more. But of course, right, as A goes, you travel along this because D equals to 2A. And so how many bifurcation value do you see? One, two, right? There are 2 bifurcation value. Right. The first is when t equal to when d equal to 0. And the second is, of course, when, you know, t squared equals to 40, right? Well, but you need to solve it in terms of A, right? You need to solve it in terms of A. So the first one, of course, is 2A equal to 0 or A equal to 0 is the critical value. And the second one is t squared equals to 4D, right? So 4D is 8A and t squared is -2, so that's 4. So A is equal to 1/2. So these are your bifurcation values. Any question? Oh, I mean, trace is the sum of diagonal, right? This is very concrete now, -2. Determinant is this. It's always that, right? But now it's a function of only one parameter A. So now we apply that to a very particular, right, structure. We don't have the abstract structure of T and D like that anymore. But still, right, it's still TD as expressed by A is the key here. Any question? Okay, so that's a introduction to this. Next class we'll repeat these ideas and you know, do more, right? Do more examples. Okay. All right. Yep. Thank you. See you next time. Wait, next week we have Tuesday schedule, but that's Thursday, so it's the same, right? Next week's Thanksgiving schedule, isn't it? So, but nothing changed, right? Because it's Tuesday or Thursday for us. Am I right? Okay. Yeah. Cool. Thanks. So see you then. You too. You too. Thank you.